And now in this lecture we'll answer on two questions. In the first question we'll find out the area of this green shape that is inside square ABCD, and in the second question we'll find out the area of this green shape that is inside quarter circle AOB. So we start with the first question. In the drawing we have square ABCD. This is angle PQC, that is a right angle. This is line segment PQ, that is equals to 2 units in its length. This is line segment CQ, that is equals to 2 units in its length. Our mission is to find out the area of this green shape. So first of all, we know that all the angles inside any square are right angles. So those four angles are all right angles. So this is a right angle. This is a right angle. This is a right angle. And this is a right angle. In addition, we know that all the sides of any square are equal to each other. So we'll define one side of this square ABCD as A. The length of one side of this square ABCD as A. So on the other side must be also equal to A. AD equals to A units in its length according to our definition. AB, side AB of square ABCD also equals to A units in its length. Side BC equals to A, and side DC also equals to A units in its length. In the next step, we define this line segment QB as X. So what is the length of the missing line segment AQ? From the drawing it is very easy to see that AQ equals to AB minus QB. So let it know AQ equals to AB minus QB. So AQ equals to AB, that is A, minus QB, that is X. So in total, AQ equals to A minus X. AQ equals to A minus X units in its length. In the next step, we define this angle. This is actually angle QCB as alpha. So in the right triangle QBC, this angle equals to alpha. This angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. AB is one side, side AB is one side of square ABCD, and therefore it is absolutely a straight line. So if you focus on this side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3, that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at this side FAB at point Q? We have this angle that is 90 degrees alpha. This is the right angle plus this missing angle. In total, the sum of those three angles must be equal to 180 degrees according to rule 3. Therefore, this first missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha equals to 90 degrees, and 90 degrees plus 90 degrees, is equal to 180 degrees. That is the sum of the angles on this side of the straight line AB at point Q according to rule 3. So this missing angle must be equal to alpha. In the right angle APQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this missing angle must be equal to 90 degrees from alpha according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, I'll copy this right triangle APQ and this right triangle QBC in a new page, and we prove that those two right triangles are similar to each other according to angle similarity rule. So actually those are the two right triangles that are going from the original drawing. So in the next step, we prove that those two right triangles are similar to each other according to angle similarity rule. So why those two right triangles similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. So actually this is angle AQP. In the right triangle AQP, and it is equal to this angle, that is angle QCB. In the right triangle QBC, they are both equal to alpha and therefore they are equal to each other. In addition, those two angles they are both equal to 90 degrees and therefore they are equal to each other. So okay, this is angle QAP. In the right triangle APQ, and it is equal to this angle, that is actually angle QBC. In the right triangle QBC, they are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles they are both equal to 90 degrees from alpha, therefore they are equal to each other. So actually this is angle APQ. In the right triangle APQ, and it is equal to this angle, this is actually angle BQC. in the right triangle QBC. They are both equal to 90 degrees one circle, therefore they are equal to each other. So if we put the total triangles of this right triangle APQ are correspondingly equal to all the triangles of this right triangle QBC, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. Triangle APQ, this is triangle APQ, is similar, this is the sign of similar, to the right triangle QBC, according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of this right triangle APQ over side QB of the right triangle QBC is equal to side AQ of this right triangle APQ over side BC of this right triangle QBC, and it is also equal to side QP of this right triangle APQ over side QC of this right triangle QBC. So repeat again. We derive that side AP of the right triangle APQ over side QB of the right triangle QBC is equal to side AQ of the right triangle APQ over side BC of the right triangle QBC, and it is also equal to side QP of the right triangle APQ over side QC of the right triangle QBC. AP is the missing side, so we know it as it is, over QB. QB is X, and it is also equal to AQ. AQ is A minus X over BC. BC is A, and it is also equal to QP, that is 2, over QC, that is 3. So in total, according to equation 1, we can find out that AP over X equals to A minus X over A equals to 2/3. So here, from this long equation, we derive that those two expressions are equal to each other. Therefore, we create equation 1 from those two expressions that are equal to each other. So according to equation 1, we get that AP over X equals to 2/3. AP over X equals to 2/3. Here we multiply this equation 1 by X, and finally we get that according to this equation 1, AP equals to 2/3 X. According to equation 1, AP equals to 2/3 X. Those two expressions are also equal to each other. So we create equation 2 from those two expressions that are equal to each other. So according to equation 2, actually we get that a minus x over a equals to 2/3. According to equation 2, a minus x over a equals to 2/3. Here we cross multiply this equation 2, and you get that according to this equation 2, 3 times a minus x equals to 2a. We'll open the brackets on this side of this equation 2, and you get that 3a minus 3x equals to 2a. We subtract 2a from this equation 2, and you get that 3a minus 2a is a, so a minus 3x equals to 0. We add 3x to this equation 2, and finally get that according to equation 2, a equals to 3x. And again, I should found out that according to equation 2, a equals to 3x. In the next step, I'll copy this right triangle QBC in the new page and we'll implement the Pythagoras theorem on this right triangle QBC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Actually, this is the right triangle QBC that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle QBC, QC squared, that is the square of the hypotenuse, is equal to QB squared plus BC squared. So I'll write it down. This will be equation 3. According to equation 3, QC squared, that is the square of the hypotenuse, is equal to QB squared plus BC squared. The hypotenuse QC is 3, therefore QC squared is 3 squared, that is 9. And it is equal to QB squared. QB is x, therefore QB squared is x squared plus BC squared. BC is 8, therefore BC squared is a squared. So in total, if we found out that according to equation 3, 9 equals to x squared plus a squared. This is according to equation 3, while according to equation 2, we have already found out that a equals to 3x. If a equals to 3x, it means that a squared must be equal to 3x squared. Therefore, we'll substitute a squared in this equation 3 by 3x squared from this equation 2. We'll do it now and you get that according to equation 3, nine equals to x squared plus a squared. A squared according to equation 2 is 3x squared. So in total, if we found out that 9 equals to x squared plus 3x squared according to equation 3. So 9 equals to x squared plus 3x squared. 3x squared is 9x squared. So according to equation 3, we have found out that 9 equals to x squared plus 9x squared. So 9 equals to x squared plus 9x squared is 10x squared. So according to equation 3, we have found out that 9 equals to 10x squared. Here we divide this equation 3 by 10. And finally we get that according to this equation 3, x equals to 9 tenths. Here we take out of this equation, and finally we get that according to this equation 3, x equals to the square root of 9, that is 3, over square root of 10 units in its length. So we found out that x equals to 3 over square root of 10 units in its length. According to equation 2, a equals to 3x. So a equals to 3x, and x equals to 3 over square root of 10. So in total, a equals to 3 times 3, that is 9, over square root of 10 units in its length. So if I found out that a equals to 9 over square root of 10 units in its length. So if we side DC, that is equal to A is equal to 9 over square root of 10 units in its length. According to equation 1, AP equals to 2/3 x. Again, according to equation 1, AP equals to 2/3 x. So AP equals to 2/3 x, and x equals to 3 over square root of 10. Here we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. After we cancel 3, we get that AP in total equals to 2 over square root of 10 units in its length. Again, AP equals to 2 over square root of 10 units in its length. This is 9 segment AP, that is equal to 2 over square root of 10 units in its length. What is the length of PD? From the drawing, it is very easy to see that PD equals to AD minus AP. So I write it down. PD equals to AD minus AP. And again, PD equals to AD minus AP. So PD equals to AD. AD is A minus AP. AP is 2 over square root of 10 units in its length. So in total, we found out that PD equals to A minus 2 over square root of 10 units. So PD equals to A. A is 9 over square root of 10 minus 2 over square root of 10. 9 square root of 10 minus 2 over square root of 10 is 7 over square root of 10. So we found out that PD equals to 7 over square root of 10 units in its length. So write it down. Here, this is 97 PD. This equals to 7 over square root of 10 units in its length. In the next step, we'll join points P and C together by straight line. By joining points P and C, we can deduct two right angles, the right angle PDC and this right angle PQC. It is very clear from the drawing that the green shape, that is the area that we are looking for, the area of the green shape, or the green shape consists of those two right angles, right angle PDC and right angle PQC. And therefore, the area of this green shape must be equal to the sum of the areas of the two right angles that it consists of. Okay, so therefore, the area of the green shape must be equal to the area of the right angle PDC plus the area of this right angle PQC. So I write it down. The area of the green shape is equal to the area of this right angle PDC, right green triangle PDC, plus the area of this right angle PQC. Repeat again, the area of the green shape is equal to the sum of the areas of the two right angles that it consists of. That is to say, the area of the green shape equals to the area of the right angle PDC plus the area of the right angle PQC. What is the area of the right angle PQC? The area of this right angle. What is the area of this right angle PDC? The area of this right angle PDC is equal to the base of the triangle that is PD times the height that is DC over 2. That's the area of this right angle PQC. What is the area of the right angle PQC? It is equal to the base of the triangle that is PQ times the height that is QC over 2. So in total, we found out that the area of the green shape is equal to the area of the right triangle PDC plus the area of the right triangle PQC. And the area of the right triangle PDC equals to the base that is PQ times the height that is DC over 2. And the area of the right triangle PQC equals to the base that is PQ times the height that is QC over 2. PC actually it is PD, the base of the triangle PDC is PD. So PD is 7 over square root of 10 times the height DC. DC is A and A is 9 over square root of 10 divided by 2. So in total, the area of this right triangle PDC equals to 7 over square root of 10 times 9 over square root of 10 divided by 2. Plus the area of the right triangle PQC is equals to PQ, that is 2, times QC, that is 3, divided by 2. So in total, the area of the right triangle PQC equals to 2 times 3 over 2. 2 over 2 is 1, so left only with 3. So the differential equals to, what is the value of this expression? Here we have 7 times 9, that is 63, divided by square root of 10 times square root of 10 is 10, divided by 2 plus 3. 63 over 10 over 2 equals to 63 over 10 times 2 plus 3. So we have 63 over 10 times 2 is 20 plus 3. So here we multiply 3 by 20 and then we divide it by 20 in order to overcome factor with this number. And we get that in total in the numerator we have 63 plus 3 times 20 is 60 divided by 20. 63 plus 60 is 123 divided by 20. Average 23 over 20, 6.15 square units. So actually, if I know that the area of this green shape is equal to either 123 over 20 square units, or in terms of numbers, the area of this green shape equals to 6.15 square units. We finished with the first question. The next step, I will present you the second question, and we solve the second question of this lecture. Our mission in this second question is to find out the area of this green shape. So, in the drawing we have a quarter circle AOB. We know that OB, side OB equals to 5 units in its length. That is to say, the radius of this quarter circle is equal to 5. In addition, we know that those three angles are all right angles. And we also know that arc AP equals to arc PQ equals to arc QB. So all those three arcs are equal to each other in their lengths. Again, our mission is to find out the area of this green shape. Okay, so first of all, we'll join points O and P together by straight line. We join points O and Q together by straight line. Because of the fact that arc AP equals to arc PQ equals to arc QB, we can implement the rule 20. So I repeat quickly on rule 20. According to rule 20, in front of equal arcs, there are equal central angles. Okay, so according to rule 20, in front of equal arcs in the circle, there are equal central angles. So in the drawing, we have a circle, and we know that arc AB equals to arc CD in its length. In front of this arc AB, we have this is central angle alpha, and in front of this arc CD we have this central angle beta. And because of the fact that those two certain angles alpha and beta are located in front of those two equal arcs, they must be also equal to each other. That is to say, certain angle alpha equals to certain angle beta. Okay, so we can actually implement rule 20 in our drawing. In our drawing, we know that arc AP equals to arc PQ equals to arc QB. In front of this arc AP, we have this is certain angle AOP. In front of this arc PQ, we have this certain angle POQ. And finally, in front of this arc QB, we have this certain angle QOB. And because of the fact that those three certain angles AOP, POQ, and QOB are located in front of those three equal arcs, AP, PQ, and QB, they must be also equal to each other. That is to say, certain angle AOP equals to certain angle POQ equals to certain angle QOB. So if we define the sides of this certain angle AOP is x, then the side of this certain angle POQ must be also equal to x, and the side of this certain angle QOB must be also equal to x because they are equal to each other according to rule 20. So, what is the side of angle, the big angle AOB? From the drawing, it is very easy to see that x plus x in total is equal to angle AOB. Okay? That is to say, x plus x is 3x. So 3x equals to angle AOB. From one side. But from the other side, it is given us the equation that angle AOB equals to 90 degrees. So we can write here that angle AOB equals to 90 degrees in its size. And from this equation, 3x equals to angle AOB equals to 90 degrees, we will derive that 3x equals to 90 degrees. 3x equals to 90 degrees. So here we divide this equation by 3, and finally we get that x equals to 30 degrees in its size. So this is certain angle AOP that is equals to x, and x equals to 30 degrees. This is certain angle POQ that is also equal to 30 degrees in size, and this is certain angle POQ that is equal to x, and x is equals to 30 degrees. And finally, this is certain angle QOB that is also equals to x, and x equals to 30 degrees in its size. In the next step, we will focus on this right angle and MOP. The right angle MOP, this angle equals to 30 degrees, this angle equals to 90 degrees, and therefore this third angle must be equal to 60 degrees in its size, according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. 60 degrees plus 30 degrees is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. It is the sum of the angles in any triangle. Likewise, in the right triangle NOP, the right triangle NQO, this right triangle NQO, the right triangle NQO, this angle equals to 90 degrees, this big angle equals to 30 degrees plus 30 degrees is 60 degrees, and therefore this third missing angle must be equal to 30 degrees in its size, according to the same rule that says that the sum of the angles in any triangle is equal to 180 degrees. OP equals to OQ. They are both the radii of the circle that is equal to 5, and therefore they are equal to each other. So OP equals to the radius R, that is 5. OQ also equals to the radius of the circle R, that is equal to 5 units in its length. So in the next step, I will copy this right triangle NPO on this, and this right triangle NQO in a new page, and we prove that those two right triangles can go into each other according to angle, side angle rule. So actually those are the two right triangles MTO and NQO that are called from the original drawing. So in the next step we prove that those two right triangles can go into each other according to angle side angle rule. So why those two right triangles can go into each other? First of all, those two angles are both equal to 30 degrees and therefore they are equal to each other. So actually this is angle MOP. And the right triangle MPO. And it is equal to this angle, that's the angle MQO. In the right triangle NQO, they are both equal to 30 degrees and therefore they are equal to each other. In addition, those two angles are both equal to 60 degrees and therefore they are equal to each other. So okay, this is angle MPO. In the right triangle MPO. And it is equal to this angle, that is actually angle NOQ. In the right triangle NQO, they are both equal to 60 degrees and therefore they are equal to each other. And finally, side PO of the right triangle NPO is equal to side QO of the right triangle NQO. They are both the radius of the circle is equal to 5 and therefore they are equal to each other. So PO equals to QO equals to the radius R of the quarter circle is equals to 5. So after prove that those two angles and the side that is included between those two angles, that is side PO, and this triangle MPO correspondingly equal to those two angles and the side that is included between those two angles, that is side QO, right triangle and QO. And therefore, we have proved that those two right triangles can go into each other according to angle side angle rule. We have those two angles and side included between those two angles, which are correspondingly equal to those two angles, and the side included between those two angles, and the right triangle and QO. And therefore, those two right triangles can go into each other according to angle side angle rule. So, I'll write it down. So, triangle MPO, congruent, this is the sign of congruent, to the right triangle NQO, according to angle side angle rule. And for the fact that those two right triangles can go into each other, we derive that they have also the same areas. Why? Because of the fact that any two triangles that can go into each other, they must have also the same areas. That is to say, the area of triangle MPO is equal to the area of this, right triangle NQO. So I'll write it down. So repeat again, if we found out that the area of the right triangle MPO is equal to the area of the right triangle NQO. Because of the fact that the area of this right triangle MPO, actually the right triangle MPO consists of two components. We define this point as point S. I repeat again, the right triangle MPO consists of two components. It consists of this quadrilateral MNSP, and it also consists of this right triangle NOS. And therefore, the area of this right triangle MPO must be equal to the sum of the areas of the two components that it consists of. That is to say, the area of this right triangle MPO must be equal to the area of this green quadrilateral MNSP plus the area of this triangle, the right triangle NSO. So I'll write it down. The area of the right triangle MPO is equal to the area of the two components that it consists of. That is to say, it must be equal to the area of this green quadrilateral MNSP plus the area of this right triangle NSO. So repeat again. The area of the right triangle MPO must be equal to the sum of the areas of the two components that it consists of. That is to say, it must be equal to the area of quadrilateral MNSP plus the area of the right triangle NSO. And according to equation number 1, the area of triangle NQO is equal to the area of triangle NQO. So this is triangle NQO. It is very easy to see from the drawing that this right triangle NQO consists of two components. it consists of this right triangle NSO, and it also consists of this triangle SOQ, and therefore the area of this right triangle NQO must be equal to the sum of the areas of the two components that it consists of. That is to say, it must be equal to the area of this right triangle NSO plus the area of this triangle QSO. So I write it down. The area of the right triangle NSO is equal to the area of this right triangle NSO plus the area of this triangle SOQ. Repeat again. The area of the right triangle NQO must be equal to the sum of the areas of the two components that it consists of. That is to say, it must be equal to the area of the right triangle NSO plus the area of triangle SOQ. So in this equation 1, we have the area of the right triangle NSO on both sides of the equation. So we subtract the area of this right triangle NSO from both sides of the equation. So the area of the right triangle NSO will get cancelled. And the left only if the area of quadrilateral MNSP is equal to the area of triangle SOQ. So if we found out that the area of this ring quadrilateral MNSP is equal to the area of this triangle SOQ. Our mission is to find out the area of this ring shape. So what is the area of the ring shape? From the drawing, it is very easy to see that the area of the ring shape equals to the area of this ring quadrilateral MNSP plus the area of this ring shape PSQ. So write it down. The area of the ring shape is equal to the area of this ring quadrilateral MNSP plus the area of this ring shape PSQ. So if you again, we shall find out that the area of the ring shape in total equals to the area of quadrilateral MNSP plus the area of the ring shape PSQ. But we already found out that the area of quadrilateral MNSP equals to the area of triangle SOQ. Therefore, we can substitute the area of this quadrilateral MNSP by the area of this triangle SQO. We do it now, and get that the area of the ring shape in total equals to the area of quadrilateral MNSP is actually equals to the area of triangle SQO. So we substitute the area of quadrilateral MNSP by the area of triangle SOQ. We have here also the area of shape PSQ. So in total we found out that the area of the green shape equals to the area of triangle SOQ plus the area of the green shape PSQ. So the area of the green shape equals to the area of this triangle SOQ plus the area of this green shape PSQ. But the sum of those two areas is equal to the area of sector POQ. Again, the sum of the green small area plus the area of triangle SOQ in total is equal to the area of sector POQ. Okay. The area of triangle SOQ plus the area of the green shape PSQ is equal to the area of sector POQ. So here, the rounded line above POQ is the sign for a sector. It means the area of sector POQ, PQO. So in total, we found out that the area that we are looking for in this question, that is the area of the green shape, is equal to the area of sector POQ or PQO. But what is the area of sector PQO? The area of the sector PQO is equal to the area of the circle that contains the sector, that is to say pi r squared times the angle between the legs of the sector, that is 30 degrees, over 360 degrees. Okay, again, the area of sector POQ, in total it is equal to pi r squared, that is the area of the sector that contains, that is the area of the circle, again, the area of sector POQ equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 30 degrees, over 360 degrees. The radius r of this quarter circle is 5, so r squared is 5 squared, that is 25, so pi r squared is 25 pi, and we have here 30 degrees over 360 degrees is 1 over 12. So in total, we found out that the area of the green shape equals to either 25 pi over 12 square units. In terms of numbers, it is equal to 6.545 square units. Okay, again, I shall find out that the area of this green shape equals to either 25 pi over 12 square units, so in terms of numbers, the area of this green shape equals to 6.545 square units. Okay. So, in the next step, I will summarize the lecture. We'll start with the first question. So our mission in this first question is to find out the area of this green shape. In the drawing, we have square ABCD. This is angle PQC, that is the right angle. This is line segment PQ, that is equal to 2 units in step. This is line segment CQ, that is equal to 4 units in step. Again, our mission is to find out the area of this green shape. So first of all, we know that all those 4 angles of this square ABCD are right angles, and we also know that all the sides of this square ABCD are equal to each other. So if you define one side, the length of one side is 8, then the length of the other side must be also equal to 8. That is to say, AD equals to DC equals to CB equals to BA equals to A according to our definition. In the next step, we define this line segment QB is B, and therefore the missing line segment AQ must be equal to AB, that is A, minus QB, that is X. So in total, AQ equals to A minus X. In the next step, we define this angle QCB is alpha. So in the right target CBQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. So this missing angle must be equal to 90 degrees minus alpha. AB is one side of square ABCD, and therefore it is absolutely a straight line. So if we focus on this side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3 that states that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at this side of AB at point Q? We have this angle that is 90 degrees on alpha, this angle is 90 degrees, and therefore this further angle must be equal to alpha, because alpha plus 90 degrees plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles on this side of the straight line AB at point Q according to rule 3. So this missing angle must be equal to alpha. In the right triangle PAQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha according to the rule that states that the sum of the angles in any triangle is equal to 180 degrees. In the next step, I prove with this right triangle APQ and this right triangle again QBC in a new page, and we prove that those two right triangles are similar to each other according to angle similarity rule. So okay, those are the two right triangles, triangle APQ, triangle QBC that they come from the original drawing. So in the next step, we prove that those two triangles are similar to each other according to angle similarity rule. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we shall prove that all the triangles of this right triangle APQ are correspondingly equal to all the triangles of this right triangle QBC, and therefore those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP of the right triangle APQ or side QB of the right triangle QBC is equal to side AQ of the right triangle APQ or side BC of the right triangle QBC, and it is also equal to side QP of the right triangle APQ or side QC of the right triangle QBC. AP is the missing side, so we will leave it as it is. QB is X, AQ is A minus X, PC is A, QP is 2, and QC is 3. So in total, according to equation 1, we actually found out that AP over X equals to A minus X over A equals to 2/3. Those two expressions are equal to each other, therefore we can get equation 1 from those two expressions that are equal to each other. That is to say, according to equation 1, AP over X equals to 2/3. We multiply this equation 1 by X, and finally found out that according to equation 1, AP equals to 2/3 X. Those two expressions are also equal to each other, and therefore we get equation 2 from those two expressions that are equal to each other. So according to equation 2, A minus X over A equals to 2/3. A minus X over A equals to 2/3. Here we first multiply this equation in equation 2, and finally found out that according to this equation in equation 2, 3 times A minus X equals to 2A. Here we open the brackets on this side of this equation 2, and finally found out that according to this equation 2, 3A minus 3X equals to 2A. Here we subtracted 2A from this equation 2, and finally found out that according to this equation 2, 3A minus 2A is A, so A minus 3X equals to 0. Here we that 3x to this equation and equation 2, and finally found out that to go into equation 2, a equals to 3x. In the next step, I copied this right angle QBC in the new page and implemented the Pythagoras theorem on this right angle triangle QBC. According to the Pythagoras theorem, in a right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle QBC that I copied from the original domain. According to the Pythagoras theorem, in this right triangle QBC, QC squared, that is the square of the hypotenuse, equals to QB squared plus BC squared. QC is 3, therefore QC squared is 3 squared, that is 9, and it is equal to QB squared. QB is x, therefore QB squared is x squared, plus BC squared. BC is 8, therefore BC squared is a squared. So in total, according to equation 3, I actually found out that 9 equals to x squared plus a squared. This is according to equation 3, while according to equation 2, we already found out that a equals to 3x. If a equals to 3x, it means that a squared must be equal to 3x squared. So we can substitute a squared in this equation, equation 3, by 3x squared from equation 2. We did it, and we found out that according to equation 3, 9 equals to x squared plus a squared. A squared is 3x squared according to equation 2. So in total, we found out that 9 equals to x squared plus 3x squared according to equation 2. 3x squared is 9x squared, so in total, according to equation 3, we actually found out that 9 equals to x squared plus 9x squared. X squared plus 9x squared is 10x squared, so in total, according to equation 3, we actually found out that 9 equals to 10x squared. Here we divided this equation 3 by 10, and so we found out that x squared equals to 9 tenths. Here we took out all those equation 3, and finally found out that according to this equation 3, x equals to the square root of 9, that is 3, over square root of 10 units in its length. Again, according to equation 3, x equals to 3 over square root of 10 units in its length. This is according to equation 3, while according to equation 2, a equals to 3x. So a equals to 3, and x is 3 over square root of 10. So in total, a equals to 3 times 3, that is 9 over square root of 10 units in its length. A equals to 9 over square root of 10 units in its length. This is to say, this is side DC, that is equal to a equals to 9 over square root of 10 units in its length. According to equation 1, AP equals to 2/3 x. So AP equals to 2/3, and x is 3 over square root of 10. So here we have 3 in the numerator and 3 in the denominator, so 3 we can cancel. And therefore, I found out that AB equals to 2 over square root of 10 units in its length. So here, this is 9/7 AP, that is equal to 2 over square root of 10 units in its length. What is the length of this 9/7 PD? From the drawing, it is very easy to see that PD equals to AD minus AP. Again, PD equals to AD minus AP. So PD equals to AD. AD is A minus AP. AP is 2 over square root of 10. So in total, PD equals to A minus 2 over square root of 10. So PD equals to A, and A is 9 over square root of 10 minus 2 over square root of 10. So 9 over square root of 10 minus 2 over square root of 10 is 7 over square root of 10 units. So in total, we found out that this is 9/7 PD, that is equal to 7 over square root of 10 units in its length. In the next step, we join points P and C together by straight line. By joining points P and C, we can deduce two right triangles, the right triangle PTC and this right triangle PQC. It is very easy to see from the drawing that the green shape consists of those two right triangles, the right triangle PDC and the right triangle PQC. And therefore, the area of the green shape must be equal to the sum of the areas of the two components that it consists of. That is to say, it must be equal to the area of the right triangle PDC plus this right triangle PQC. So again, if we found out the area of the green shape in total equals to the area of the right triangle PDC plus the area of the right triangle PQC. The area of the right triangle PDC equals to the base that is PD times the height that is DC over 2 plus the area of the right triangle PQC. The area of the right triangle PQC equals to the base that is PQ times the height that is QC over 2. So again, the right triangle PDC is PD times DC over 2, and there are another PQC, PQ times QC over 2. PD is 7 over square root of 10, QC, this is 9 over square root of 10 divided by 2. PQ is 2, QC is 3 divided by 2. So what is the value of this expression? We have 7 times 9 is 63, square root of 10 times square root of 10 is 10 divided by 2. Here we have 2 in the numerator and 3 in the denominator, so 2 we can cancel, and we have only with 3. 63 over 10 over 2 equals to 63 over 10 times 2 plus 3. 10 times 2 is 20, so this expression total equals to 63 over 20 plus 3. Here we multiply 3 by 20 and then we divide it by 20 in order to common factor with this number. We know that we have in the numerator 63 and 3 times 20 is 60 divided by 20. 63 plus 60 is 123 divided by 20. So if we know that the ratio equals to either 123 over 20 square units, or in terms of numbers, the area of this green shape equals to 6.15 square units. So we finish with the first question. In the next step, I presented to you the second question, then we solve the second question of this lecture. Our mission in the second question is to find out the area of this green shape. So in the drawing, we have quarter circle A or B. OB equals to 5, therefore the radius of this quarter circle equals to 5 units in its length. In addition, we know that those three angles are all right angles, and we also know that arc AB equals to RPQ equals to RQB. So in the first step, we join points O and P together by side line, and we join points O and Q together by side line, and we join points O and P together by side line. So here we can implement rule 20. So we can implement rule 20, according to rule 20, in front of equal arcs, there are equal central angles. So in front of equal arcs in the circle, there are equal central angles. So in the drawing, we have a circle, and we know that arc AB equals to arc CD. In front of this arc AB, we have central angle alpha. In front of this arc CD, we have this central angle beta. And because of the fact that those two central angles alpha and beta are located in front of those two equal arcs, they must be also equal to each other. That is to say, central angle alpha equals to central angle beta. So we can actually implement rule 20 in our drawing. Because we know that arc AP equals to RPQ equals to RQB. In front of this arc AP, we have this is central angle AOB. In front of this arc PQ, we have this central angle POQ. And finally, in front of this arc QB, we have central angle QOB. And because of the fact that those three central angles AOP, POQ, and QOB, they are all located in front of those three equal arcs AP, PQ, and QB. They must be also equal to each other. So if we define one central angle as x, then the other two central angles must be also equal to x because they are equal to each other. So central angle AOP equals to x, central angle POQ equals to x, and central angle QOB also equal to x. It is very easy to see that the sum of those three central angles, in total, it is equal to the big angle, angle AOB. That is to say, angle AOB equals to x plus x plus x, that is 3x from one side. But from the other side, we know that angle AOB equals to 90 degrees because AOB is a quarter circle. So, and from this equation, 3x equals to angle AOB equals to 90 degrees. We will derive that 3x equals to 90 degrees. Here we divided this equation by 3 and found out that the missing angle x is equal to 30 degrees in its size. So central angle AOB P equals to 30 degrees, side triangle POQ equals to 30 degrees, and side triangle QOB also equals to 30 degrees in size. In the right triangle MPO, this angle equals to 30 degrees, this angle equals to 90 degrees, and therefore this quadrilateral must be equal to 60 degrees in size according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the right triangle NOQ, this angle equals to 90 degrees, this angle equals to 30 degrees plus 30 degrees is 60 degrees, and therefore this quadrilateral angle must be equal to 30 degrees in size according to the same rule. OP equals to OQ, the above the radius of the circle that is equal to 5, and therefore they are equal to each other. So the next step, I copy this right triangle MPO and this right triangle NQO in the equation to prove that those two right triangles can go into each other according to angle side angle rule. Okay, those are the two right triangles MPO and NQO that are going from the original drawing. So while those two right triangles can go into each other. First of all, those two angles are both equal to 60 degrees, and therefore they are equal to each other. In addition, those two angles are both equal to 30 degrees, and therefore they are equal to each other. And finally, side OP of the right triangle MPO is equal to side OQ of the right triangle NQO. They are above the radius of the circle that is equal to 5, and therefore they are equal to each other. So I should prove that those two angles and the side that is included between those two angles, that is side OP and the right triangle NPO, correspondingly equal to those two angles and the side that is included between those two angles, that is side OQ and the right triangle NQO. And therefore, we should prove that those two right triangles can go into each other according to angle side angle rule. We have two angles and the side that is included between those two angles in this triangle that are correspondingly equal to those two angles and the side that is included between those two angles in this right triangle NQO. So therefore, those two right triangles can go into each other according to angle side angle rule. And from the fact that those two right triangles can go into each other, we will derive that they have also the same areas. This is to say the area of triangle MPO is equal to the area of triangle NQO. So in a minute, we found out that the area of the right triangle MPO is equal to the area of the right triangle NOQ. The right triangle MPO consists of two components. It consists of this green quadrilateral MNSP, and it also consists of this right small triangle NOS. And therefore, the area of the right triangle MPO, in total, it is must be equal to the sum of the areas of the two components that it consists of. That is to say, it must be equal to the area of the green quadrilateral MNSP plus the area of this right triangle NSO. Once again, if I found that in total, the area of the right triangle MPO equals to the area of quadrilateral NSP plus the area of the right small triangle NSO. Likewise, we have right triangle NQO. This right triangle NQO consists of two small triangles, the right triangle NSO plus this triangle SOQ. And therefore, the area of this right triangle NQO must be equal to the sum of the areas of the two components that it consists of. This is to say, it must be equal to the area of this right small triangle NSO plus this triangle SOQ. Repeat again, the area of the right triangle NQO must be equal to the sum of the areas of the two components that it consists of. That is to say, it must be equal to the area of the right triangle NSO plus the area of triangle SOQ. So here we have the area of triangle NSO on both sides of equation 1. So we subtract the area of this right triangle NSO from this equation 1, and we left only with the area of quadrilateral MNSP that is equal to the area of triangle SOQ. So here, this is the green quadrilateral MNSP, and the area of this green quadrilateral MNSP equals to the area of this white triangle SOQ. Our mission is to find out the area of this green shape. From the drawing, it is very easy to see that the area of this green shape equals to the area of this green quadrilateral MNSP plus the area of this green small shape PSQ. And again, the area of the green shape equals to the area of the green quadrilateral MNSP plus the area of the green small shape PSQ. But we already found out that the area of quadrangle M minus P is equal to the area of triangle SOQ. Therefore, we can substitute the area of quadrangle M minus P in this equation by the area of triangle SOQ because they are equal to each other. We did it, and we should find out that the area of the green shape in total equals to the area of triangle SOQ plus the area of the small green shape PSQ. Then again, we should find out in total the area of this green shape is equal to the area of this right triangle SOQ, white triangle SOQ plus the area of this green shape PSQ. But the sum of the areas of those two components is equal to the area of sector POQ. So in total we can find out the area of the green shape equals to the area of sector POQ. The green shape in total is equal to the area of sector POQ. Here the rounded line above POQ is the sign for a sector. It means the area of sector POQ. But what is the area of this sector POQ? The area of any sector is equal to pi r square. That is the area of the circle that contains the sector times the angle between the legs of the sector over 360 degrees. And therefore the area of the sector POQ must be equal to pi r square. That is the area of the circle that contains sector POQ times the angle between the legs of the sector that is 30 degrees over 360 degrees. So again, the area of the sector POQ equals to pi r square times 30 degrees over 360 degrees. R, the radius of this quarter circle R is equal to 5, therefore R square is 5 squared, that is 25. Therefore pi r square is 25 pi, and 30 degrees over 360 degrees is 1 over 12. So in total we can find out the area of the green shape equals to either 25 pi over 12 square units. So in terms of numbers, the area of this green shape, that is the area that we are looking for in this question, is equal to 6.545 square units. Okay, thank you very much.